Lesson: Reinforcement Learning Fundamentals. Reinforcement learning, a pivotal aspect of machine learning, focuses on how agents should take actions in an environment to maximize cumulative reward. This concept is central to the development of intelligent systems capable of making decisions autonomously. Reinforcement learning is distinguished from supervised learning by its focus on learning from the consequences of actions rather than from explicit examples. This approach is particularly useful in scenarios where it is not feasible to provide explicit instructions or where the environment is too complex to model accurately. Pause. The core of reinforcement learning lies in the interaction between an agent and its environment. The agent receives observations about the state of the environment, takes actions based on a policy, and receives feedback in the form of rewards. The goal is to learn a policy that maximizes the expected cumulative reward over time. This process is often modeled as a Markov Decision Process, which provides a mathematical framework for modeling decision-making in stochastic environments. A practical example of reinforcement learning is its application in game playing, most notably demonstrated by AlphaGo, developed by DeepMind. AlphaGo's ability to defeat human world champions in the game of Go showcases the power of reinforcement learning algorithms. The success of AlphaGo is attributed to the combination of deep neural networks and reinforcement learning techniques, specifically the use of value networks and policy networks to evaluate board positions and select moves. Reinforcement learning can be categorized into model-free and model-based approaches. Model-free methods, such as Q-learning and policy gradient methods, do not assume knowledge of the environment's dynamics and learn directly from interactions. Q-learning, for instance, learns the value of state-action pairs and updates these values based on the rewards received. This approach is particularly suitable for environments where the model is unknown or too complex to model explicitly. In contrast, model-based methods involve creating a model of the environment's dynamics and using this model to plan actions. These methods can be more sample-efficient but require accurate modeling of the environment. Practical implementation of reinforcement learning requires the use of specialized tools and frameworks. OpenAI Gym is a widely used toolkit for developing and comparing reinforcement learning algorithms. It provides a standard API for environments and a diverse collection of benchmark problems, ranging from classic control tasks to complex simulations. TensorFlow and PyTorch are popular frameworks for building and training the neural networks used in reinforcement learning algorithms. These tools offer high-level abstractions for constructing computational graphs and automatic differentiation, which are essential for implementing complex models. Reinforcement learning has been applied to a variety of real-world challenges beyond game playing. In robotics, it is used to develop control policies for tasks such as locomotion, manipulation, and navigation. For example, reinforcement learning algorithms have been employed to train robotic arms to perform complex manipulation tasks, such as object grasping and assembly. In finance, reinforcement learning is used to develop trading strategies by modeling the stock market as an MDP and learning policies that maximize profit. This approach allows for adaptive strategies that can respond to changing market conditions. One of the key challenges in reinforcement learning is the exploration-exploitation trade-off. An agent must balance exploring new actions to discover their potential rewards and exploiting known actions that yield high rewards. Techniques such as epsilon greedy and upper confidence bound are commonly used to address this trade-off. Epsilon greedy involves selecting a random action with probability epsilon and the best known action with probability 1 epsilon, while UCB selects actions based on their potential for high reward and uncertainty. Another significant challenge is the issue of credit assignment, which involves determining which actions are responsible for received rewards. Temporal difference learning and eligibility traces are techniques used to address this challenge. Temporal difference learning updates value estimates based on the difference between predicted and actual rewards, allowing for more efficient learning from delayed rewards. Eligibility traces extend this concept by assigning credit to sequences of actions that lead to rewards, providing a more nuanced approach to learning from delayed feedback. Reinforcement learning is a rapidly evolving field with ongoing research aimed at addressing these challenges and expanding its applicability. Advances in deep reinforcement learning, such as the development of deep Q networks and proximal policy optimization, have significantly improved the performance of reinforcement learning algorithms on complex tasks. These algorithms leverage the representational power of deep neural networks to handle high-dimensional state spaces and learn complex policies. In conclusion, reinforcement learning provides a powerful framework for developing intelligent systems capable of autonomous decision-making. By leveraging tools such as OpenAI Gym, TensorFlow, and PyTorch, professionals can implement reinforcement learning algorithms to tackle real-world challenges across various domains. Understanding the core principles and challenges of reinforcement learning is essential for developing effective solutions and advancing the field. The continued development of novel algorithms and techniques promises to expand the scope and impact of reinforcement learning in the coming years.